All right, let's dive right into this explainer and discover how your everyday allergy medications are meticulously designed, almost like microscopic machines. Have you ever wondered why popping a single tiny pill can just shut down a severe allergy attack? Well, it's definitely not magic, it's precise, deliberate chemical engineering. Today, we're going to look at the exact molecular blueprint of H1 antihistamines. We'll see how chemists essentially build these molecules piece by piece so they interact directly with your body's receptors. Now, to understand how these drugs actually work, we rely on something called the structure-activity relationship, or SAR for short. Think of SAR as our master architectural guide. It allows us to draw really important conclusions about how a molecule's specific structural requirements completely dictate its optimal activity and its pharmacological actions. Essentially, SAR tells us what every single atom does and exactly why it's placed where it is. It's like a building. If you swap out a single support beam, the whole structure changes. And the exact same principle applies right here.
So here's our blueprint for today. We're going to systematically tear down the generic antihistamine block by block, starting with the blueprint itself, then looking at the dual aromatic engine, the vital connection, the crucial carbon chain, the terminal nitrogen anchor, and finally, how we fine-tune the molecule.
Starting off with part 1, the universal skeleton that all of these medications share, which is broken down into 4 distinct, interchangeable parts.
Moving right into part 2, the dual aromatic engine, which really builds the foundation for how this drug interacts with our biology. What's absolutely wild about the starting point of our molecule is the strict requirement here. You absolutely have to have 2 aromatic groups, labeled R1 and R2, to drive the molecule's affinity to the H1 receptor. I mean, it's totally non-negotiable for the drug to be active. These aromatic groups usually take the form of phenyl, benzyl, phenyl, or pyridyl rings. And sometimes you'll see an aromethyl or a hetero-aro group acting in this role, kind of like what we see in drugs like diphenhydramine or doxylamine. The golden rule we get from our SAR is that the nucleus of the antihistamine absolutely must bear a minimum of 2 of these alkyl or aryl functions, or it needs an equivalent structure embedded directly into a polycyclic ring. This dual engine setup, that's what actually initiates the connection with your body's histamine receptors. Next up, part 3, the vital connection, which acts as the molecule's spacer. This is where the chemistry gets really elegant. Those aromatic engines have to be linked to the rest of the drug via a connecting atom, which we just call the X group. Swapping out just one single connecting atom at this X position completely defines the class of the drug. For example, if we use a nitrogen atom as our spacer, we get the ethylene diamine category. That gives us drugs like triplenamine or pyrolamine. But if we swap that nitrogen out for an oxygen atom, we instantly shift to the amino-alkyl ether derivatives, and that includes incredibly common over-the-counter meds like diphenhydramine. Finally, if that connecting atom is a carbon, we're looking at the monoamino propyl derivatives, which includes phenyramine and chlorphenyramine. It is honestly amazing how a single atomic substitution alters the entire chemical category, all while preserving that essential spacing function the drug needs to actually work. That brings us to part 4, the crucial carbon chain, which is the precise link connecting that X spacer to our final anchor. Now you might be thinking, what happens to our allergy medicine if we decide to tinker with it? What if we stretch out or branch this specific carbon link? Does it make the drug stronger, or does it just break it completely? The answer is right in the structure-activity relationships. If we keep it to a simple 2-carbon ethylene chain, so a CH2 attached to another CH2, we hit the sweet spot for maximum allergy relief. That precise exact length is essential. But if chemists branch this chain or expand it to make it longer, it generally results in a way less potent allergy drug. But wait, here is the fascinating twist. Expanding that chain, a process called homologation, actually opens the door to developing entirely different classes of drugs. By stretching that simple chain, scientists can transform a basic antihistamine blueprint into powerful neuroleptics and tricyclic antidepressants. So a tiny structural shift literally redefines what the molecule does inside the human brain. How cool is that?
Let's move to part 5, the terminal nitrogen anchor, which secures the drug at the very end of our structure.
This specific part of the molecule is absolutely mandatory for antihistamine activity. We need a basic terminal amine function here, specifically a tertiary amine, usually a dimethylamine group. This tertiary amine acts as our anchor because of its very specific chemical properties. It's highly basic, with a pKa hovering between 8.5 and 10. And why does that matter to us? Well, in the environment of your body, this basic nature ensures the nitrogen becomes protonated. It basically takes on a positive charge when it binds to the H1 receptor, firmly locking the drug into place. Plus, from a manufacturing perspective, this terminal nitrogen allows for salt formation, meaning your medication stays perfectly stable in solid form while it's sitting on a pharmacy shelf. But chemists didn't just stop at a simple dimethylamine group. Sometimes they take this terminal nitrogen and embed it right into a basic cyclic or heterocyclic ring system. By altering the position of the amino group into a ring like this, they can actually boost the antihistaminic activity even further. This is a brilliant little structural maneuver that gives us highly effective, really potent drugs like cyclazine, chlorcyclazine, and Maclizine. Finally, part 6, fine-tuning the molecule. We have the machine built, but how do we maximize its potency? This is where the true elegance of molecular engineering really shines through. Let's revisit our aromatic engine for just a second. By simply plugging in a single halogen atom, something like chlorine or bromine, or maybe an OCH3 group into the precise para position of the pheno ring, the parent molecule gets a massive boost. It acts like a supercharger. For example, taking the base drug phenyramine and introducing a single chlorine atom completely transforms it into chlorphenyramine, which is a significantly stronger medication.
And it's not just about what atoms are present, it's about exactly how they're oriented in 3D space. Antihistamines often exhibit optical isomerism, meaning the molecule can exist in left-handed or right-handed shapes that are literal mirror images of each other. The SAR reveals that the dextroisomer, the right-handed orientation, vastly supersedes the left-handed levoisomer in potency. We see this all the time with drugs like dexchlorphenyramine or dexbrompheniramine. It just proves that tiny spatial tweaks, literally just mirroring the geometry of the molecule, yield massive, real-world clinical results.
As we wrap up this explainer today, I want to leave you with this thought to ponder. We've seen how swapping an oxygen for a carbon, extending a chain by just one link, or flipping the 3D orientation of a compound completely dictates whether a molecule cures your allergies, acts as an antidepressant, or does absolutely nothing at all. Isn't it incredible how the exact, invisible geometry of these medicines fundamentally dictates exactly how our bodies heal and react? Understanding the structure-activity relationship isn't just chemistry. It's honestly uncovering the very language our bodies use to communicate with the world around us. Thanks so much for joining me on this molecular journey today. Keep questioning, keep learning, and I'll catch you in the next explainer.